Hi, everyone. Welcome to the webinar, our 2020 Dyslexia Update, New Science and Solutions. What I'd like to do now is introduce you to the presenter, Dr. Martha Burns. Dr. Martha Burns is our Director of Neuroscience Education at Scientific Learning. She has authored 4 books, including a brand new book titled Cognitive and Communication Interventions, and over 100 journal articles on the neuroscience of language and communication. Her expertise is in all areas related to the neuroscience of learning and language and the science of reading. So without further ado, let's get into the webinar. I will hand everything over to Dr. Burns.
Thank you so much, and welcome everyone to our webinar today. What we're going to really start with is talking about reading and the brain to get you caught up, and I'm going to go through it from a couple of different perspectives. But probably most of you realize that learning to read requires a whole new link in the brain between what we hear and what we see. As you probably know, there were many centuries where most human beings did not read. And even 1,000 years ago, the individuals who read were primarily in religious fields or in some kind of documentation of some kind. And it's only been the last 100, 150, 200 years where we've had a majority of individuals who read. So we had to rewire the brain when we want to be able to read the text. So you have the green, you see the regions involved in spoken language, and the regions that are very important for listening and hearing speech. And then the red areas are the visual cortex, where we're going to see the letters, and we're going to have to link the letters to sounds with an area you can see at the bottom that's called the visual word form area. And then we have other kinds of areas in the brain that are very important for attention and handwriting and gestures. And all of those are going to have to become linked together. And that takes time. So reading has to be taught. It isn't acquired and just naturally developed the way we might develop language or other kind of athletic kinds of skills and things of that sort. And this is a nice schematic, I think, because it shows that reading acquisition requires fast recognition of letter strings, and they're often called graphemes, and it establishes a functional link with areas that are important for speech, which are phonemes, the sounds. So initially, children decipher words, that's the yellow pathway, and they effortlessly analyze every word and convert every letter into a sound, grapheme into a phoneme. So if I were to read the way a young child learning to read English would read, that would go, how, to, s, e, m, b, o, a, s, t, it. And that's very slow and that's very tedious. And so year after year, what happens is reading automates and the words take more of a direct unconscious route. And that's that green route that you see there, which allows faster access to the lexicon and to meaning. So teachers in the beginning and early elementary grades focus on developing this ability to decode, but then they have to build up the automaticity through a lot of reading practice and through language skills and through actual linking of all of these areas within the brain so they're a nice cohesive network. And that takes time. But often in the English language, we say children are learning to read essentially from grade 1 until grade 4 or 5. And then by grade 5, we're hoping that they're starting to read so well and so efficiently and so rapidly that they're reading to learn. But there's another component to the reading circuit, and that is what we call spatial attentional scanning. We have to be able to read. We have to be able to move visually from left to right, if it's the English language. We have to be able to sequence the sounds in order and recognize the letters and recognize the orientation letters. And Stanislas Dehaene, who's the neuroscientist who wrote Reading in the Brain and then more recently has just written How We Learn, Better Than Any Machine, has has done a lot of research showing the importance of this visual word form area and how it has to become linked to our language areas, and that takes time. But the earlier a child is exposed to written words, let's say that a baby is being read to, or a young child, a toddler is being read to by their parents, the link between the visual word form area and the language areas is building even before a child is explicitly taught to read. But the importance of orientation and the spatial orientation visually can be exemplified when we think about how we can recognize an object, even a complex drawing. So here you see a pretty complex drawing of a horse, and one of the images, the silhouette has 2 stars and one of them has 1. But no matter what orientation that occurs, whether it's on its side or kind of upside down, or no matter what parts are missing or taken away, you still recognize it. And all of you could very quickly, no matter how I showed you this image, could recognize it. But that's not true of letters. So as you all know, and many children confuse them, a B and a Q and a D and a P and a G are all circles with lines going in different orientations, but that totally changes the meaning of what we're reading. And a lot of children, many children have to sort that out, and some have trouble with that visual component as well. So I put Google on there because we all recognize Google and we know the colors, but it wouldn't be unusual for a child to maybe say goggle instead of Google, or gobble instead of Google, because those orientations of those letters to them don't mean anything for a while. They have to learn that. So the reading brain then involves these language areas. The left, it's called the superior temporal gyrus. Gyrus is just bump. So it's just the top bump of the temporal lobe that's very important for language. That B area that's blue is called the supramarginal gyrus, and it links actually what you see with what you hear. So it's an integration region in the left hemisphere. And then you see the bottom of the temporal lobe that's green, and that link to vision, that visual word form area that's really very important, and that's part of C. And then other areas like you see D there, which is part of what we call the hippocampus, which is really important for long-term memory. So it's kind of our file clerk. So when you're reading and you're trying to think of a word or trying to guess a word maybe that you haven't seen before, you're going to go to the hippocampus, and that's going to help you to get access to other aspects of meaning. So reading is not real simple. It's pretty complex, and there are different components when we're teaching reading that have to be mastered, and a child can struggle with any one of those components or several of them. So one is this phonological representation, this ability to understand that letters have sounds associated with them. One is phonological awareness, which is a little different, which is the ability to parse a word into its sounds. So to know that the word catch, for example, k, a, ch, has 3 sounds, but it has more letters than that. So parsing words into sounds is not exactly the same as phonological representation, and children have to learn both. They have to be able to map the sound to the letter and backwards and forwards. So they have to know that the letter B makes the B sound. And if they see the B, they know it's B. But if they hear B, they know they can convert it to a B. They have to be aware of grammar and grammatical endings, prefixes and suffixes, and how those are attached to words and how those are sequenced within words, and change the meaning. And then they have to be able to write it all and relate the whole word to meaning, and then whole sentences to meaning. So there's a lot that goes on. And what I'm going to be sharing with you is some of that newer research on what we know about some of the issues that may lead to difficulties in those areas. And we'll talk about that. There are also then all of these areas of the brain have to be connected together. And it's only been about 10 or 15 years where we could really look at these fiber tracts in use. We could look at parts of the brain. We had functional imaging that we could start doing in the 90s, where we could see, oh, this child's using this part of the brain and this child's using another part of the brain, or maybe all of these parts. But about 10 or 15 years ago, we were able to actually see the fiber tracts as well and start documenting those. And there are a lot of fiber tracts that we now have identified. They're the highways within the brain that link them together. And if you think of these regions all working together in the brain for us to be able to read, and it's like a network that you might have on your cell phone, where you have somebody that's in your network that's in California, and somebody that's in your network that's in Florida, and somebody that's in your network in Canada. But we're all communicating in real time. And that's how the brain works as well. And in our case, the electronic waves that are allowing us to communicate are the transportation avenues, but in the brain, it's these fiber tracts. And we can identify fiber tracts just like we can identify regions that maybe aren't as strong or maybe aren't as fast. And we'll talk about that in a minute. So all of this initially, a great description of this was done by Scarborough, and he called it the simple view of reading. That skilled reading involves at least two major components, which is the ability to recognize words. And to do that, you have to be able to sound them out, decode them, and know that words are parsed into sounds. And then you have to understand the language. You have to know what the word means, and you have to know what the grammatical ending means, and you have to know what the way the words are constructed into a sentence and how that works. So you need language meaning on one side and word recognition on the other. But new research indicates that the simple view of reading is much more complex. And that even though we all would love to simplify it because it would make our teaching easier, that we don't have single entities like that. And they aren't isolated. So reading is multifactorial, and it changes, and it's malleable, and it depends a lot on different contexts. And that was published by Hugh Katz a long time ago. But also recent research indicates that skilled reading is contingent on general oral language skills. Nation had a wonderful publication on that. It's in your bibliography, on the importance of language. If we don't have language skills, a student can't superimpose reading on language that doesn't exist. We also know from research by Snow and review articles by Snow that the knowledge of academic language and reading and reasoning is really important in older students. So when we get into adolescence, for example, where they're reading to learn, that's where their knowledge base is critical. They may be able to sound out lots of complex words, but if they can't attach meaning to them, or they can't quickly get access to that meaning, then they can't learn from what they've read, and then they struggle. And then finally, we know that there are additional cognitive skills that are components of reading that we've kind of put on the back burner for a while, but that are really essential. The ability to attend, very specifically to prefixes and suffixes, and the ability to remember what you've read and hold on to it. So when you're on page 14 of a text, you can remember what you read on page 1. Those are some skills we kind of used to take for granted, but we now know they're core components of effective reading. And a lot of these involve what we call executive functions, these cognitive skills. So recent achievement research suggests that executive functions, this ability to regulate yourself, and by regulating yourself, it means that you can have some self-control in thought and action, and that you're goal-directed. So when you sit down to read a book, you're just not going through and decoding it, but you're actually taking notes, let's say, or you're actually trying to link it to what you already know and apply it to things that you know. All of these components, and you're You're able to sit there and stick with it for a while. You have some patience to get through what you have to read, and you have some what's called persistence, the ability to keep going, perseverance through difficult text material. All of that, those are executive functions, and they're all important in reading achievement, especially in this aspect that we talked about of moving from learning to read to reading to learn. Executive functions, as I said, just to go into them a little bit more specifically, involve attention. And one of the terms that psychologists use is response inhibition. That means that when I'm paying attention, when I'm focused on the task, I'm also able to ignore distractions in the environment. I'm also able to ignore impulses that maybe I want to get up and walk around, or maybe I want to get up and call a friend or something, or an email comes in, and I can ignore all of that and I can stay focused. So when we talk about response inhibition, we're talking about ignoring distractions, being able to sit and be patient and consistent. Another one is updating and monitoring of working memory. And what that means is as I'm reading, I'm also thinking, oh, yes, I remember that character on page 5. And oh, yeah, I remember that situation on page 15. And I remember that the teacher talked about that in class last week. So yes, and maybe some of us would underline that word, or we might write a little note to remind us. But all of that is that updating and monitoring. And we do it a lot internally, and that's referred to as working memory. And then also we need a lot of flexibility, because we need to be as we're reading, we may make an assumption of what we just read, or think a word means something. And then we realize, I think I misread that. And we go back and we read it again. Or also the ability to, when I am reading, to rethink what I thought I knew, and to say, wow, that's interesting. I never thought of it that way, or I never looked at it that way. All of those are executive functions, and they're critical to reading comprehension, but they're also critical to achievement in school. And so they work together. And one of the reasons that students who read easily find school easy is because those two are working together. For our students who are struggling to read, they have this double task of not being able to learn easily from reading, and then also not being able to easily attend and easily hold on to what they've read. And it becomes troublesome. We've had a lot of professions that have really gotten into this in recent years. The speech language pathology profession had an article written, this is a Journal of Speech and Language Hearing Research in 2016 by Montgomery, Gillum, and Evans, on the importance of memory and attention skills in reading, and how we didn't used to think about that. We used to concentrate more on, in the back, if you will, that was their image. But in the past, we thought more about language and phonology. And coming forward, we're just including more of these cognitive skills, which means that the simple view of reading can now be updated. We can view it a little bit more with this eye on the complexity by looking at those two bottom circles or ovals that originally were part of it, the word recognition, phonological awareness, and decoding part. But also know that there are some other components to add to that, especially understanding the alphabet and sound symbol recognition. And on the right-hand side of the simple view of language, when we're looking at our simple view of reading, when we're looking at language comprehension and vocabulary structure, also adding some other components that we've learned are very critical. Rapid naming, rapid auditory naming, and the ability to name quickly and easily, we know is associated with reading skill and reading fluency. And then also this ability to encode, meaning the ability to write as much as to read, to be able to read and then think out, to take notes, or to be able to verbalize ourselves what it is we've just read. And then all of the areas at the top, that new circle, which is the current research on cognitive executive functions, working memory, response inhibition, cognitive flexibility and reasoning. So let's get in now. This is a dyslexia workshop. So let's get into the students who struggle to read and what we know about that now and where we are. First of all, when students struggle to read, it's the process of learning to read that is initially rife with frustration. So almost all children who are struggling with reading have been struggling since they first started to try to read. And they are left susceptible to adverse secondary outcomes, anxiety and depression, we know from research by Nadine Gabb, because because school becomes so hard for them. We think of reading and language arts as kind of isolated subject areas, but if you have trouble reading, you're going to have trouble with math because you're going to have trouble with math problems. You're going to have trouble with science because you can't read the text. You're going to have trouble with social studies and history and all of the subject areas that depend so much on your ability to read. So when students struggle with reading, it creates a lot of anxiety, especially around school and achievement. So the term dyslexia has been around a long time, and it's originally comes from the Greek word meaning abnormal or difficult, which is the dys part, and then lexis with words. So difficulty with words would be the original meaning of dyslexia. And it was used, and this is the area that I originally specialized in, was stroke and brain injury. And it was originally used, alexia and dyslexia were used when we talked about individuals who couldn't read because they had some kind of a brain injury. But the term has been adopted and it's been applied to children who are having trouble learning to read. And the most common criteria over the last 20 to 30 years was called the discrepancy criteria. And the discrepancy was where you looked at a child's overall potential to learn, essentially usually their IQ, and then you compared that to their actual reading achievement. So if a child had, let's say, an IQ of 120 or 110, but they were in the 5th grade and they're reading at the 2nd grade level, then that standard deviation that you'd see, that deviation between their potential and their reading would be enough to have qualified them to be diagnosed as dyslexia. But what we're going to talk about in a minute or so is the new ways that this is being looked at and the new criteria. We also do know, though, that early indicators of dyslexia can be seen, and a lot of this research has been done by Nadine Gabb, but can be seen with problems with rhyming when they're young. So early problems with phonological awareness, trouble with perceiving words, thinking one word is one thing and then it's actually another thing, or using an incorrect word when they're young for something that sounds kind of like it. Saying, for example, gobble for goggle or something like that. That they have trouble in the early years with sound symbol recognition, trouble learning the alphabet. Then in the early years when they're being taught to decode, they can't sound words out easily. This rapid naming skills that we now see associated with it, and then also problems verbalizing, problems hearing something and being able to tell it back and that kind of thing, which leads, of course, to difficulties with reading fluency because they read e, a, d, n, f, so slowly and laboriously. If they've had a lot of decoding work done, reading comprehension then suffers because if you're reading slowly and laboriously, it puts a much bigger demand on your memory and you can't hold on to it. And then many of the children have language problems to start with. They had trouble learning language, so reading comprehension is affected by that. They're not really sure what those words mean. Reduced vocabulary that would go along with that. Difficulty with content knowledge. Many of those students, Stanislaus DeHend has shown, many of those students sit in a classroom and are not good at listening in general and listening to a teacher talk. And 80 to 90% of classroom instruction is teachers talking, students listening. So if a student's having trouble with language, having trouble with processing the information quickly and easily, that becomes an issue. Then if they're supposed to read on the side, obviously that adds to that. And then obviously from that, a decline in overall school performance. So moving away from the discrepancy model of defining dyslexia, the more current view is to look at it from what we call a multi-deficit approach, meaning that there's a lot going on. It's complex, and you could have lots of different aspects that could be contributing to a child's difficulty reading. And there's a wonderful quote that I'm going to take from Stanislas Dehaene's new book on how we learn. And the quote is, if we don't understand how children learn, how can we understand how to teach? And I want to emphasize that, because if we don't understand what these issues are that contribute to having trouble learning to read, then what happens is we don't know how to teach the children around that. And that's why it's important to emphasize that. So from the multi-deficit approach, we can look at it essentially, and you can see the reference that this is taken from now, the Osternaz, Palchik, Wang, and Nadine Gabb research. But we have genetics. I'll talk about those. It's not huge. It's not that you can predict that somebody has a gene, they become dyslexic, but there are genes that increase the risk of having trouble learning to read. We also have brain level differences. It is the brain that reads. So obviously, if you're having trouble reading, there are going to be things that are different about the way your brain is organized. We'll talk about that. There are definitely perceptual and cognitive components to reading that are essential for being able to read quickly and easily and learn to decode especially. And then environmental factors, and we'll address all of those. So the risk factors, again, are genetic predisposition. Again, not that there's a gene that we would say, well, if you have this gene, you might have dyslexia. Nothing like that, but just risk factors that we'll talk about. So it does run in families. Brain level differences, perceptual and cognitive level differences. And here we get into some of the newer research at the surface level, RAN, which is this, the reading or the rapid naming, letter knowledge, vocabulary knowledge, things we can see when we're actually working with the child, atypical phonological awareness. And then below the surface, other perceptual functions, executive function issues, difficulties learning language, and difficulties with rapid auditory processing, being able to hear speech sounds quickly and easily. And then environmental factors. We know that children who come from low SES environments are more likely to have difficulty learning to read. That may be because of lack of exposure to books or lack of access to books within the home. In some cases, it could also be, and a lot of people feel a big factor is stress in the home. Children of poverty have a lot of stress in their home environment, and stress interferes with higher levels of the brain's ability to organize, because when you're under stress, your brain is trying to solve the situation that's causing your stress. But we could also have issues of less effective schooling or interventions, and that might appears to be an issue as well. So again, why is this important? Well, if we only deal with reading issues, it can take years for a student to catch up, and some never do. So I talked about above the surface and below the surface. I've adopted a dyslexia iceberg kind of graphic to illustrate this. What we see is what we can measure. We can measure phonological awareness. We can measure phonemic awareness. We can measure sound symbol recognition. We can measure alphabet knowledge, decoding skills, rapid naming. But, and that's important, but that doesn't mean that that's what you only work on. It's like if you have a rash, you can put calamine lotion on, but if you don't get at what's causing the rash, the calamine lotion isn't going to get at that. And so we also have to look at these under the surface components of environmental factors, perceptual factors, and brain level differences and genetic factors as well. So we know, okay, if you have this gene might predispose you to having a little bit of trouble with rapid auditory processing. Another gene might mean that visual skills are different. So by understanding the genetics better, by understanding brain level differences better, and by addressing environmental and cognitive and perceptual issues, we can get at the whole child and at the whole process, and we can remediate and get the student reading faster and more effectively. And that's really what it's all about. Just for a few facts from the genetic standpoint, as I said, developmental dyslexia is strongly heritable. Most of the people, I have dyslexia in my family, and so we're very careful to watch our grandchildren and look for signs that might suggest that there could be some dyslexia there too, because it does tend to be passed on, and it does run in families. And the sooner you know that, the sooner you can get working on some of those skills in children. That in our family, it's decoding that's one of the issues. So we can work with our young grandchildren very early on decoding skills, just to make sure that any genetic predisposition they have, we're getting on top of it before they ever even get to school. So 50% of children with a sister, brother, mother, or father with dyslexia will receive a diagnosis themselves. That's pretty high. And 68% in identical twins. And this is taken from research that Nadine Gabb did and published in 2017. And then there are some specific genes that I've listed for you that right now are known to be important drivers of brain development and are associated with dyslexia. Again, it doesn't mean that that they cause dyslexia. It just means that they increase the risk. And new research corroborates that infants at genetic risk for dyslexia, if you actually look at infants who have a genetic risk, and this was research out of Goswami's lab, they exhibit differences in early responses to language. This was just published a few months ago, but they did some experiments with infants with word learning. So what they did is they had 19-month-old infants, really toddlers, that were at risk for dyslexia, and because one parent had dyslexia. And then what they did is they had the students learn words associated and mapped these novel words to novel references. So they just looked at how these 19-month-old toddlers were able to map new words and learn new words. And what they saw is that the students who weren't, the children who weren't at risk showed a long time where they looked at the reference and they looked at the new words. But the children who were at risk for dyslexia showed a difference. And you can see over on the graph on the right, NAR is the not at risk infants, and AR is the at risk infants. And what you see is just they didn't even spend as much time even looking and trying to figure out what the new word and the referent was. They just weren't as interested, you could say, in words, but it's not fair to say interested. It's just that that's not one of their strengths. In terms of brain level differences, this came from this I have referred to before, because this particular issue of Neuroscience and Education from August 2016, which is open access, by the way, is where that multi-deficit view of dyslexia is very carefully outlined. But one of the things we now know is that we have brain regions that make up the reading network that we can identify relatively quickly, relatively easily, and we can see structural differences in children who have dyslexia. New research that just came out again this year, Conan et al., found that the visual word form area, that part of the brain that we have to link to what we hear, is also not developing in the same way. There's a reduced activation in this visual word form area when you have individuals who have dyslexia. And it's apparent when they are discriminating, when they're hearing sounds. So if you look at youth with dyslexia, you can see that the visual word form area is not activated when they are listening to sounds, whereas with individuals who don't have dyslexia, it is. That link between auditory and vision is very intact and very rapid. So the authors conclude that the primary deficit in at least a subset of children may lie early in the speech processing stream with categorical perception, the ability to tell the difference between a p and a t and a k and a k, okay? To hear it and to hear it easily. We also see brain level differences in the way that the brain creates these bumps and grooves, cortical folding. Because you have a fixed skull, as the brain gets bigger and bigger, it folds in on itself. And we do see abnormal age-related cortical folding in children who have a diagnosis of developmental dyslexia. And then we also have research, this is out of Gabrielli's lab. John Gabrielli's been studying dyslexia in language for many, many years from a brain science standpoint. And here you can see three major white matter tracks. The longitudinal fasciculus, that just means the long fiber track. The arcuate fasciculus is in blue. That links that sound to speech and the ability to create symbols. And then that purple, it's called the superior longitudinal fasciculus. It just means it's the top fiber track. Arcuate fasciculus just means it's shaped like an arc. So these are major fiber tracks in the left hemisphere that are very important for linking sound to meaning and sound to production and word recognition. And you can see the differences in children who have a diagnosis of dyslexia. There are also this is again that arcuate fasciculus, that arc-shaped one. If you go back here, you can see it's blue there as well. And even in very young children, before they're starting to develop any signs of dyslexia, but they have a history of dyslexia, and that's FHD plus that you see there means family history of dyslexia is present. And you can see that the arcuate fasciculus, when they are young, long before they ever would present with a dyslexia, is already not as thick and mature. Now, does that mean it's damaged? No, it just means that we're going to need more work to get it to develop. The brain is an experience-dependent organ, so we're just going to have to power more effort and more work into building that. But that's child is still very capable of learning to read. And we all can also see that same area, that same fiber track, the arcuate fasciculus, is also associated with language skills. And so this came out, this was a preprint that came out this last fall, just about a year ago, 2019. And then one other important fiber track is the fiber track that links sound to speech. And by that, what I mean is your thalamus is very deep in your brain, and it's the gateway to your brain. And the thalamus has nuclei that route information. So when you hear something, the first thing that happens is that stimulus goes to your that sound goes to your thalamus. The thalamus decides, is it speech or is it not speech? And if it's speech, it sends it to the left hemisphere. And if it's slow like music, it'll go to the right hemisphere. Thalamus does the same thing with vision. If a ball is being thrown at you, you need to process that differently than if you're looking at a cup and trying to figure out where to pick the cup up. And so the cup is a static visual stimulus, and so you don't need to process it quickly. But if a ball's coming at me and I want to catch it, I have to process it very quickly. And so there are fiber tracks for that, that route the information. And what we found is that in children with dyslexia, the fiber track that enables you that routes the rapidly occurring information to the left hemisphere, and speech is very rapidly occurring, is not as mature, is not as thick, is not as well developed. Can it be exercised? Yes. Can it become stronger? Yes. So there are differences and similarities between these issues that we see. I've talked a lot about what we see with English-speaking children and reading children, but we also see it in other countries. And I was listening to a neurodiversity seminar yesterday, and one of the women was talking one of the speakers was talking about how Chinese individuals who have dyslexia have different issues from the brain standpoint. Well, some of their issues are a little different, but some of them are very the same. So you can see here research by Feng in 2019 shows that there are some shared differences that we see across languages, whether you're talking about Romance languages like French or English or ideographic languages like Chinese. And that these neural correlates may vary a little bit, but generally speaking, a lot of them have to do with speech sound perception, rapid auditory processing, and these cognitive skills like working memory and attention. So what do we do about it? That's why you're all here, and where do we go? And really what I want to start with is how important education is. Reading has to be taught. Reading isn't something, there are a very small subset of children who can teach themselves to read, but the vast majority of all of us have to be taught to read. And so educators change brains, and they drive the brain to be a reading brain. But it's important for educators to understand the importance of the perceptual and cognitive level differences as well. And more pre-reading research on this. This was by Chrisman et al. In 2015, published again in the Journal of Speech, Language, and Hearing Research, is the importance of auditory processing prior to school entry. The sooner we can get these children that might be at risk and start building up their auditory processing skills, their ability to perceive rapid changing sounds, their ability to discriminate from a d, from a g, from a j, all of those capacities can be exercised, and they can be exercised in young children. And we know that in many children who are eventually diagnosed as dyslexia, these are a subset of problems that they do exist. It's also important to keep in mind that English, especially as a language, is what we call non-transparent, which means that we have lots of alternate spellings for the same sounds. This means that many children have trouble learning to spell, but they also have trouble learning that the F sound itself that we see from the letter F in phone is also the sound that PH can make, or also the sound that other combinations occur in, especially vowels. And you can see this was a George Bernard Shaw quote, that you could spell fish as P-H-O-E-T-I. The F sound in phone, the I sound in Phoebe, and the sh sound in nation. Now, obviously, that's not how we would ever spell it before, because for the sh to be a TI, it has to be with a certain morphological ending. But kids don't know that, and students don't know that. And so English becomes very complex, and we have a lot of children who struggle with learning to read because English isn't a transparent level language. At the cognitive level, we've talked a lot about this, the importance of executive functions. There's an article by Donnelly and Christensen outlining that when you see children who have dyslexia, often they have problems with response inhibition. They're easily distractible. They're up and around, having trouble sitting and sustaining attention. They have a lot of trouble remembering what they hear as the sounds in words, so that they'll misunderstand what somebody said because they can't hold on to all the sounds they said. They'll have trouble with verbal working memory, holding on to the meaning, and then often also visual working memory, which will affect their ability to spell. It'll affect their ability when they go into any kind of ability to write. And then they often have some problems with cognitive flexibility as well. But here I want to depart a little and remind you that each of us is very different. Our human brain is very complex. My brain isn't like your brain. Any of you who are married know that your brains are very different from your significant other. And these differences and this very complex organ that has both genetic influences and experiential differences. We've all had different experiences growing up. We all had different parenting. We all had different exposures. All of that means that there are also going to be a lot of individual differences in dyslexia. So I might have 5 students who are diagnosed with dyslexia based on testing that's done and very careful documentation of some of the things they're having trouble with. But one of them might be a superb athlete, and the next one might be a superb musician, and the next one might have remarkable social skills, and they all might. And some of them might have some visual issues and some of them might not. So we're starting to go to what, again, this conference I attended, the Stanford conference this weekend, that people are referring to as personalized approaches to intervention. Medicine is going that direction, you probably have noticed. So if you have a diagnosis of a cancer, for example, they don't treat you the way they treat everybody who has the same diagnosis. They actually do a genetic assay and they look at other aspects to see which interventions would be personalized to your specific issue. And we're getting that way in our intervention with dyslexia as well, and it's very important. So if reading's difficult for a child, one of the things that happens is that child will read less. And because that child will read less, they may build other skills, and those skills are important, but they don't necessarily translate to academic success. And so we can see an increase in behavioral issues associated with our students that are because of their academic struggle. And we need to consider the importance of getting to these children as early as possible and intervening as quickly and as effectively as we can. So each child is unique, each student is unique. We've got to look at their perceptual strengths and weaknesses, and we have to look at them individually. Do they have good verbal skills? Do they have good phonological skills? Do they have nonverbal skills? What are they? What are their auditory perceptual capacities? What are their visual? What are their sensory motor? What are their cognitive strengths and weaknesses? And then what are their language strengths and weaknesses? And also, and I got this also from the course over the weekend, the Stanford neurodiversity course, is that there are strengths that many individuals with a diagnosis of dyslexia have, and we need to capitalize on that. And in the vocational world, in the work world, they found that many individuals with a diagnosis of dyslexia are terrific entrepreneurs. They're very creative. They're very good at starting new businesses and getting them going and working with people. They have a lot of creativity. And good, solid goals. They're good with visual reasoning very often, and they may have some unique practical skills, storytelling ability, visual spatial skills. If you want to read more about this, it's not in your bibliography because I just added this slide last night, but it's by Nancy Doyle, published in 2020 in the British Medical Bulletin, and it is actually open access, so you can get in and get that if you want. So what should instruction include then? Number one, you have to be taught to read. So all children need explicit, direct instruction that's systematic, sequential, and cumulative, and it follows a logical plan. It also needs to meet the specific needs of the student. So if it should be intensive and highly concentrated in the areas that each student is struggling with. If a student's struggling with decoding, work on decoding. But if they're struggling with perception, work on perception. If they're struggling with working memory, work on working memory. We need the instruction to be meaning-based and purposeful. We want the students to feel like they're reading for a reason and enjoy reading. And we want instruction that incorporates a simultaneous use of both of the auditory and visual pathways. We don't want to just work on one pathway only. And we need other instructional approaches that are determined as appropriate by whatever the school or the diagnostic team has come up with. Specific reading approaches that we can address then are the phonological decoding approaches. And you have a lot of programs out there that specialize and focus on decoding, Orton-Gillingham-based approaches. But don't forget, you're also going to need language comprehension, vocabulary instruction, and it's got to be very specific and it's got to be very strong. And we also want to build cognitive skills in these children, want to build their working memory and build their attentional skills and build their flexibility in thinking. All of this is even more important for our adolescent readers. So while it's important to develop specific skills in the early ages for learning to read, it's even more important in our adolescents who are expected to read to learn. And making sure that you have these executive functions as part of your instruction is very important. And this is an article that just was published in 2019. So this is where I want to go to neuroscience technology. Neuroscientists like Stanislas Dehaene, like Michael Merznick, like Paula Talal have been working for the last 25 years on carefully designed technology that gets at all of this simultaneously, that builds underlying capacities, executive function skills of attention and working memory, also has the phonological component, and then includes the rapid auditory processing and sequencing components that drive the brain through exercises to work on many skills at the same time. This is just one example I'll show you. This is a phonological awareness task called Bear Bags, where the child, in this case, has to listen, look at a word and listen to the last sound, the final sound in the word, and then find one of the pictures below that has the same last sound. So here you see it.
Mud.
You can hear. Mud. So the final sound is the same as in bed, and the child would click on that.
Mop.
Mop. The final sound is a p, same as cup.
Note.
Note. The final sound is the same as in hat.
Jab.
Final sound is the same as in pub. Now below, the student can
Did.
click on and identify any of these words below that they may not be sure of before they get started. Notice there's a start button where they press it to get going in the first place. And that actually has been upgraded recently in a new version of this where it actually says go. And that means the student is in charge of when they get the stimulus, and that drives some neurological attentional neuromodulators called acetylcholine. The student immediately knows whether they got it right or wrong. If it's correct, they get a reward and a point. If they get it wrong, they're shown what the correct one is. So they get instant feedback. All of this is happening to the student at every single response. So it's individualized. It's designed specifically for that student. If they get 3 in a row right, they get to move forward and they get more words and harder ones. If they get one wrong, it moves them back. And so it adapts to every single student. And that's where that personalization comes in. Now, as the students get older and they're working on sight recognition of high frequency words, this works on the visual tracking as well from left to right, as well as working memory. They have to hold the word in mind and they have to wait patiently. So it's also an attentional exercise until the right word, the matching word comes about. We'll see that one.
Click the fish with the matching word.
Sure. Idea. Next. Sure. Yet. Next. Yet.
And what you can see again is you're working multiple, the advantage of neuroscience-based technology is you can work at multiple levels. You can be working at the cognitive level with working memory and attention. You can be working at the visual processing level with the words flying across a page. And you're also working on this explicit instruction of high frequency word recognition quickly. And they get faster and faster as the student gets better at this. Again, it adapts individually to every student. There are exercises that are designed specifically for secondary students that work on a lot of these same skills. In addition, working on skills like the ability to remember different aspects of grammar and language and vocabulary. And all of these overriding tasks, also some of them include just speech sound discrimination, just this rapid processing of sounds for those students where that is an issue. And in this task, this is for secondary students. They're in a lab and they have all sorts of different kinds of visual things, but they press on a bubble in this case, or sometimes it's an amoeba, or sometimes it's something like that, but they press on it and they hear a sound like ba, 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 da. In a second it changes, they have to click on it. And that's working on this categorical perception that you saw all this research showing a lot of individuals have trouble with. So in conclusion, thank you for joining and sticking with us, but the fundamentals of mastery-based learning are built into the Fast Forward neuroscience programs that I just showed you, and components, providing a unique path for each student. And we use the algorithm of mastery because one of the things neuroscience interventions can do is they can be game-like, so they're highly motivational, they're highly adaptive. Every single keystroke adapts so that the student's moving forward, but also reviewing things they have trouble with. They're socially safe because it's in their own world, on their own tablet or their own computer. No one else knows what they had trouble with, only they know in the computer. It trains all of these skills simultaneously so you can have a huge impact as an intervention very quickly and very effectively. It is effortful. I mean, they really have to work hard. They have to listen. They have to pay attention. It's quite rigorous. So it's building up their tolerance for working hard and their self-advocacy and self-efficacy. They say, yeah, I can do this. I can do this. I can work hard. I can master this. And the end product is it yields rapid word recognition and robust comprehension in a relatively short period of time. You're talking about a few months of this intervention to see some great results. So this came from The Economist, but I think it's a good way to summarize this, that education technology, together technology with teachers, this doesn't substitute for good teaching, but it can revamp schools. We see changes in the human brain. What you see on the left are the average of 35 of 7-year-old second graders who are typically reading. You see 2 areas light up. We see the red area is the part of the brain that reads aloud and encodes, if you will, is able to convert the letters into sounds and then actually use them. And then the back part of the brain is the part, that blue circle is where you see letters and sounds and the symbols combined. You see in the middle picture that children who have these 7-year-olds who have trouble with reading, they're reading impaired, those areas are not lighting up in the same way when they're doing a phonological awareness task. But in this case, just after 8 weeks of the Fast Forward intervention that I've shown you and talked about, those areas become activated. So the brain in that respects become normalized, and so do 2 other regions that are very important for reading, that visual word form area that we've talked a lot about, and then the part of the brain that kind of is so important for language and perception. So what you can see is in a short period of time, the brain can become much more like it is in a typical reader, and those students can then learn to read and then read to learn. And we see the evidence of that reading to learn in several studies, but this is one school district, a high poverty school district in New Orleans after Katrina. You can see that the school district that you see in orange was below the state average for their general high stakes testing. But after they instituted the Fast Forward program in 2006, and then they added reading assistant, which is reading aloud with an computer-assisted reading approach. You see, whoops, sorry, I'm going to go back to that slide. You see that they not only got the students in their district up to the state average, which was also increasing, but that they eventually rose above the state average. So the effects last, and they move from learning to read to reading to learn. And when students can read to learn, you see the changes across all subject areas. So what you see is not only English language arts in the upper left-hand corner, but science, math, and social studies. And the students are efficient then in their academics. So thank you so much for attending. If you have any questions for me or any questions about the Fast Forward programs or any of the research, please just send those to webinars@cylearn.com and we will get back to you with answers as quickly as we can. Thank you again.